Okay, in this video we're going to focus on the zeros of polynomial functions, and a zero is actually a concept that we're already very familiar with. It's the same thing as an x-intercept, but this time we're going to formally kind of refer to it as a zero. So we say if f is a polynomial function, so maybe this is our f of x right here. Let me see if I can get this. There we go. It wants to right now. This is our polynomial function f of x right here. Then we say that it's possible that it has zeros. We say the values of x for which f of x is equal to 0 are called the zeros of the function f. So in other words, a zero, if we wanted to know what a zero is, its definition is this right here. It's all x values that cause this to be true. In other words, when I plug this in, I get that. And so we're going to give a zero another name. The first thing we're going to do is we're going to refer to a zero as an x-intercept because it's going to make our lives a whole lot easier. As a matter of fact, we're going to give it some other names here. And so if you've got a highlighter, let's just do this. We say a zero is the same thing as an x-intercept, is the same thing. We say these values of x are the roots or solutions of the polynomial equation f of x equals 0 here. So we say that zeros are the same things as roots, are the same things as solutions, are the same things as x-intercepts. So we say each real root of the polynomial equation appears as an x-intercept on the graph of the polynomial function. All of these things come together to basically mean that we already know how to find these. It's just that we're going to give them a new name now, and we're going to hold them, in high value because they're very valuable. So we say, looking at this equation here, we say f of x equals this cubic thing right here. What I want you to see is that it's just this polynomial function you see here on the left. And so when I look at this picture here, and it indicates that -3 is an x-intercept, and -1 is an x-intercept, and +1 is an x-intercept, I know that these have to be zeros or roots or solutions of this polynomial equation right here. And so in terms of finding them, of course we could get them by graphing this, but really we haven't spent a lot of time graphing it. We're building up to that. For right now, we want to say, how do we find these algebraically? So to find zeros, finding zeros, here's what we're going to write. Step 1, set y equals f of x equals 0, okay? Set either of these things, however it's written, equal to 0. And then what we're going to do is solve for x. And I want to put a few things down here under solve for x. We're going to start by factoring all the time. I mean, factoring is going to be the way to go if we can help it. If factoring doesn't work, we say then if quadratic, this is really important, then quadratic formula. There we go. Essentially, you're going to knock it down to something quadratic, and then you're going to, if it doesn't factor there, then we'll just use a quadratic formula. It's really easy to do. So setting this equal to 0, let's go ahead and start with this. I noticed that this has 4 terms to it, so I'm going to try to factor this by grouping. So I'm going to group my first 2 terms here. I'm going to say plus now, and remember this negative here on this third term right there has to stay with that x. But you get this, and we say, okay, well, what do these first 2 terms have in common here? Well, I notice they both have an x squared they can give. I'm left with x plus 3, and I want to be left with another x plus 3 over here on the right if this factors, and it does. So I'll take out a -1 here, and we get left with now just an x plus a 3. And because both of these have an x plus 3 now, we're going to take that out front. We say x plus 3 times x squared minus 1, and then this right here I notice is a difference of squares. So I get x plus 3, x plus 1, x minus 1. We say here's our factored thing, and because this times this times this equals 0, then we say either x plus 3 equals 0, or x plus 1 equals 0, or x minus 1 equals 0. And without showing my work here, you can see how solving this you get x is -3, and that was an x-intercept on the graph. We just had to set y equal to 0 and go solve for our x-intercepts here. So we say, yeah, I get -1 here and +1 here for my zeros. And those are certainly on the graph as well as x-intercepts. So we're going to be looking at those graphically as x-intercepts, but everything else we're just going to solve algebraically. So that's my intent, is to solve a couple more here in this video. We'll talk about the zeros of these functions here. So when we talk about the zeros of this function here, we say f of x equals x cubed plus 2x squared minus 4x minus 8. This looks like another situation where, first of all, we want to get a 0 in for our y value. Plug in 0 for y to find the x-intercepts. We're going to solve this by grouping. So we get x cubed plus 2x squared plus -4x minus 8. And so factoring out our greatest common factor here, we get x squared, x plus 2. Here it looks like I would factor out a -4, so plus a -4 times this would be an x plus 2. And then this x plus 2, we'll just take it out from, we say x plus 2, and then we get left with x squared minus 4, which itself is a difference of squares. So that becomes x plus 2, x minus 2. So an interesting thing happens here. we're going to set each of these factors equal to 0. And one of my favorite things actually happens here. X plus 2 equals 0, x plus 2 equals 0, or x minus 2 equals 0. I get from the first two here, I get negative 2, and I get negative 2, and then from here I get positive 2. So I get 3 answers, but one of them repeats. And we're going to come back to that right there. It's a repetition of a 0. And then this last one here, it says find all zeros for this. Well, again, we'll plug in 0 for y, and we're going to solve this. And again, we're going to start by factoring, which I noticed there's a GCF here. We're going to go ahead and factor out the GCF of x squared. And I get left with x squared minus 4, which, of course, x squared minus 4 is a difference of squares, so x plus 2, x minus 2. So I can't factor this anymore, but one thing I am going to write here is this, and I do want to write this as it is newts, but we'd say, here we go. We would say that this is technically x times x. And so when we write all these factors equal to 0, we actually get x is 0, or x is 0, or x plus 2 is 0, or x minus 2 is 0. You can see that there are 4 total factors in this product here. So setting all 4 of them equal to 0, we get x is 0, or x is 0, or x is negative 2 here, or x is positive 2 here. So our solutions, we would just write them this way: 0, 0, 2, and negative 2. And you could write plus or minus 2, but those would be the solutions here. So when we talk about the zeros of a function and their x-intercepts being the representation of those zeros or solutions, then let's talk about what happens when you get the same answer more than once. So the multiplicity of a 0. We say there are times at which a polynomial function can have the same solution repeated more than once. We've seen this happen in this last video. Here we got negative 2 twice, and here we got 0 twice. So when that happens, we say that it changes the multiplicity. So we say a 0 that occurs only once is said to have a multiplicity of 1, but a 0 that occurs n times is said to have a multiplicity of n. So however many times something happens, we say that's the multiplicity of that 0. So considering this function here, we say finding its zeros. Again, we'll set y equal to 0, plug in 0 for y, and I get negative x to the 4th. Actually, let's just factor this. I notice that this looks a little bit different for a trinomial. Everybody here has a negative in common and 2 x's in common. I'm going to factor out a negative x squared. And what I get left with is positive x squared minus 4x plus, and I suppose this would be a 4 here. And then looking at this, I'd say, well, that factors right there, right? So what we get here is this: we get a perfect squared trinomial where this is x minus 2 squared. And you know what, if that's really kind of throwing you through a loop, we'll just write it this way. We'd say x minus 2 would be the factors of this right here. So having it written, either this way, which is common, or this way, we could say, or even factoring it even further, negative x times positive x times x minus 2 times x minus 2. Essentially what I want everybody to see is when you set these equal to 0, when you set negative x equal to 0, and you set x equal to 0, and then you get x minus 2 equal to 0, and then you set that, again equal to 0, what you get for answers here are these answers. We say 0, 0, 2, and 2. And so we would say that 0 has a multiplicity of 2, and 2 has a multiplicity of 2. So graphically, how does this have any significance on our graphs here? What I want everybody to see is that when we have even multiplicities, that is, when these answers occur here, we got 0 and 2 for our answers. When they occur an even number of times, it will not cross. Will not cross the x-axis at any 0 having even multiplicity. And so this is going to be, let's see, multiplicity. It's going to be good news when we graph these, because it's going to help us kind of know a little bit more about the graph before we go and actually sketch it ourselves. So we say if R, they use the letter R here. R is a 0 of even multiplicity. Okay, so this will be our 0 here. And it has even multiplicity. Then we say the graph touches the x-axis and turns around at R. Kind of like our graph turned around here and did not cross the x-axis. Whereas over here on this graph, let's take a look at it. We'd say that it, we got 3 answers here. We got negative 3, negative 1, and positive 1. They all occurred once. So our graph crosses there. We say even multiplicity, then it won't cross. We say if R is a 0 of odd multiplicity, then the graph crosses the x-axis at R, regardless of whether the multiplicity of a 0 is even or odd, though. We say graphs tend to flatten out near zeros with multiplicity greater than 1. Okay, which just means if you have a 0 that happens a lot of times, your graph flattens out kind of right next to it. Okay, So this is good to know about our multiplicity here in our graphs, because as we get into the next videos here, we'll talk about how to sketch these. So for right now, let's talk about this. We say find the zeros of this function and give the multiplicity of each zero, and then state whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. So when you look at something at this, like this for the first time, it's really intimidating. But what I want everybody to see is this. We have something where if we're going to find the zeros, we're first of all going to set y equal to 0. But we have something that's been given to us in a factored form. So it's worth writing a note here. We'd say that this is already factored. And that's really our primary solving method, is to factor something. So since this is factored, what we're going to say is we're going to set all the individual factors equal to 0. And actually, we could divide both sides by -4 in this case, and still end up with this here. Now, what I want you to notice, though, is that we really have x plus 1 squared, which really means this. And we have x minus 5 squared, which really means this. So when we're setting these factors equal to 0 and solving, like x plus 1/2 equals 0, I don't have to really set that equal to 0 on paper twice just to tell you that it will happen twice for each of these. But here I get x equals -1/2, and here I get x equals 5. So we're going to make a little note here. We're going to say that this has a multiplicity of 2. And the same is true for our 5 over here. This is a multiplicity of 2. And so we're going to make a little note here. We're going to say will not cross x-axis at these x values. And because we have even multiplicity at each. Cheers.